Welcome. In this lecture, we will talk about Brownian motion, atomic models and structure, the periodic table, atomic variations, elements, compounds, and mixtures, and briefly we will discuss antimatter. Brownian motion. The idea of atoms goes back to 5th century Greeks, but the idea was squashed by Aristotle only to be revived in the 1800s by an English meteorologist and schoolteacher, John Dalton, who explained chemical reactions by proposing that all matter is made of atoms. But he didn't have any evidence for his assertion. It wasn't until, in 1827, the Scottish botanist Robert Brown, while he was looking through a microscope at pollen, which was immersed in water, he noticed something even more interesting. That the pollen was bouncing around in random fashion, as I've tried to illustrate here, with this pollen particle bouncing around in water, assuming the background of the slide is water. Now, pollen particles are not alive, so if we're imagining this particle being just immersed in water, what is causing this motion? That was the question that Robert Brown had to ask. And what's really causing the motion is collisions between the visible pollen particles and invisible particles, which would be the atoms. They're invisible in that we can't see them with the naked eye, can't see them with the microscope, but the effect of the atoms on the pollen that we can see was not too small. We could see that effect. We could see the random motion being caused by the collisions. We may not have been able to see the atoms colliding with the pollen, but we saw the result of the atoms colliding with the pollen. Now, this type of motion, this random motion, has become known as Brownian motion, of course named after Robert Brown. And this type of motion is described mathematically through what is known as a random walk. Now, in 1905, Albert Einstein, in the same year he published his paper of special relativity and the photoelectric effect, published a paper mathematically modeling Brownian motion and relating his model to physical quantities. And he came up with this equation, which is known as the diffusion equation. And here we have the density of Brownian particles. So, for example, the pollen particles, the density of those. And this d is the diffusion coefficient. And now this is a partial differential equation, so I don't expect anyone in this course to understand this at all with regard to the mathematics. I'm going to go through some steps and just get to an end result and then explain something. You don't need to know the math behind any of this, but I think it's fascinating, so I wanted to take a moment to talk about it. This equation can be solved for the density of Brownian particles. The solution to this diffusion equation, and we're looking at the solution right now, is a normally distributed probability density. And it's okay if you don't know the lingo I'm spewing, it's not important for the course. We can find the conditional average of the position along the x-axis. So we go through some stuff, and I'm just going to write this out. We're going to do some integration, we're going to get some results, and then I'm going to explain why it's significant. Now, if you have taken calculus, you know that if you try to integrate this, we have an odd function and an even function, and therefore automatically, and it's over an even interval, and so this will just produce 0. If we want to find instead the average of the square distance from the origin, assuming we're looking just at a single dimension, the x dimension, that result can be integrated to something that's non-zero because we have an even function and an even function integrated over an even interval, and we get this, 2d times t. This x squared with the bar over it, where the bar means the mean or the average, this is known as the mean squared displacement, which is the average of the squared displacement of the particle from the origin. Now, why is this significant? The MSD, or the mean squared displacement, is an experimentally measurable quantity. The diffusion can be extracted, or the diffusion coefficient, this capital D, can be extracted from experimental measurements. Why is that important? Because if you extract this, you can actually use that D to determine physical quantities, other physical quantities. So let's draw a plot. Let's say you're taking real experimental measurements, and you're just plotting them out. You're plotting the mean squared displacement versus the time. So how far away is the particle getting as time progresses? That's essentially what this plot is. And then you can draw a linear fit to this. And then you use that and you can extract the diffusion coefficient from this experiment. Again, why is this significant? Well, Einstein came up with the equation. You could solve for the diffusion coefficient if someone were to come along and do experiments, which they did later. And from this diffusion coefficient, Avogadro's number can be determined, and the approximate size of molecules and atoms can be determined. And this is way before you could experimentally pick up an atom and move it around. That didn't come till many, many years later. So this is an important, very, very significant theoretical result that has real-world consequences, positive consequences. Okay, so let's take a moment to, this is like a spoiler slide for what's to come, but we're going to break down the atomic structure. So again, it's a spoiler slide. So let's begin with the nucleus of an atom and then some electrons. In the nucleus of an atom, which I've illustrated by the red circles and the black circles, consists of protons and neutrons. The protons are the positively charged particles, and the neutrons are the neutrally charged particles. So they don't have a charge. They're neutral particles. Now, both the protons and the neutrons, which compose the nucleus, are not elementary particles. In fact, they are composed of something more fundamental. Now, the electrons, which are orbiting, technically this orbit that I've drawn is not correct. One of the circles should be perpendicular to the other, but that's not important for this current discussion. Now, the size of an atom is roughly an angstrom, and an angstrom is simply 10 to the negative 10 meters. So very, very small. So here is a proton. Now, the proton itself is much, much smaller than the total size of the atom. It's 10 to the negative 15 meters. And a proton, as I said, is not an elementary particle. Now, what does that mean? It means that it is composed of other smaller particles. And those particles are known as quarks. So a proton is composed of 2 up quarks and 1 down quark. Now, we're not going to go into a lot of detail regarding quarks. Just know that protons are composed of quarks. So protons are composed of even smaller particles known as quarks. The same goes for neutrons. Neutrons are also not elementary particles. They are composed of smaller particles known as I mentioned already for the proton, as quarks. Protons and neutrons are roughly the same size. Now, you'll notice that in the quarks, I have an up quark and a down quark. Don't worry about the color because there's color charge and all this other stuff going on. But each individual quark contains a particular amount of charge. Adding the charge up produces the net charge of these larger particles, namely the proton and the neutron. So let's look at the down quark. And just quarks in general are very, very small. They're smaller. They're less than 10 to the negative 18 meters. Now, the down quark has a negative 1/3 charge of an electron. Whatever the electron charge is, and an electron is by nature negative, the down quark also has a negative charge, but it's the magnitude of its charge is only 1/3 of that of the electron. And the up quark is actually positive, and it's with a value of 2/3 of the electron charge. And again, knowing the details of the up and the down quark is not important for this course. Just know that protons and neutrons are not elementary particles because they are composed of smaller particles called quarks. Electrons, on the other hand, are, as far as we know, elementary particles. Electrons are elementary particles just as quarks are elementary particles. Now, overall, even though these particles get smaller and smaller, even the atom itself, with the quarks, the protons, the neutrons, the electrons, even an atom is too small to see with visible light. And it's simply because the atom is smaller than the wavelength of visible light. So just keep that in mind. You can't see an atom regardless of how good your optical microscope is. You will never be able to see an atom using visible light. You have to use other tools. Let's talk about atomic models. Again, I said the previous slide was a bit of a spoiler and gives a little bit too much away, I would say, for what might be exciting that comes next. But I wanted to get that discussed and then go forward with kind of a step backwards, I suppose, talking about atomic models. Now, what is a model? In general, a model is an abstraction, pictorial, mathematical, or both, that helps scientists visualize what can't be seen and enables predictions to be made. Now, in the previous slide, you saw a pictorial model. An atom doesn't really look like that. In fact, we don't really know exactly what an atom looks like because we can't see it with visible light. So we have to create models. The previous slide had a pictorial model. Physicists and mathematicians come up with mathematical models, and they connect it with a pictorial model. One of the earliest models is the Rutherford-Bohr model. And this was presented by Niels Bohr and Ernest Rutherford in 1913, so quite a long time ago. And they proposed that The atom is a system consisting of a small, dense nucleus surrounded by orbiting electrons. Very similar to like the solar system, where you have planets orbiting the sun, but instead here you have an electron orbiting the nucleus. And instead of the electron being held in orbit by gravitational forces, like the planets are held in orbit around the sun, the electron is held in orbit by electrostatic forces, something that we will talk about later in this course. Now, in this model, electrons were said to only be able to occupy very, very specific orbits, which were called shells, which corresponded to their energy level. This idea of an energy level and an electron being in a particular, I would say, quote-unquote, orbit related to the energy level, that is true, at least in part. And we'll talk more about that. Something I want to mention is that the radius corresponding to the lowest energy is known as the Bohr radius, and it's symbolized by A0. But as I mentioned, there are various energy levels. This is the lowest energy level. So the electron is not limited to this single orbit. So let's just pretend that this model is perfectly correct, which it's not, but there are a lot of things about it that are correct. This is the lowest energy level, but there are many others that it can move to. But in order for the electron to actually move to a different orbit, each successive orbit corresponds to a higher energy level. Protons in the center of an atom, which are at the nucleus, are positively charged, and the electrons are negatively charged. So these two are pulling on each other. The nucleus is pulling the electron close to itself. So in order for the electron to jump up to the next energy level, you have to give the atom energy. So you give the atom energy, the electron jumps up, and then the electron eventually fall back down again. And when it does so, it will release light or electromagnetic radiation, whether in the form of visible light or not visible light. These energy levels, which I've drawn here as circles, are numbered simply as 1, 2, 3, etc. And these numbers are called principal quantum numbers, denoted by the symbol n. So we have n equals 1 at the lowest level, n equals 2 at the next level, and then n equals 3, and so on and so forth. The smaller the value of n, the lower the electron energy. When n equals 1, the electron is said to be in the ground state. Now, the number of electrons allowed to be in these individual energy levels is limited. You can't have an infinite number of electrons in the ground state, for example. A finite number of electrons are allowed to reside on each of these individual levels. For example, if we have 3 shells, 2 electrons can be on the first shell, 8 can be on the second shell, and 18 can be on the third shell, and etc. Now, what I mean by etc., well, this continues this pattern. Now, what is the pattern? The pattern is that the maximum number of electrons allowed in each energy shell corresponds to 2 multiplied by the energy shell number squared. Now, atoms can have a maximum of 7 shells. So that means the highest n value you can get is n equals 7. So the bigger your energy level, the more electrons that level can hold. And there's deeper reasons behind this, which we will not even get close to touching on in this course. So let's zoom back in. As a reminder, we have so far discussed just the Rutherford-Bohr model. Next, we have the cloud model. Now, this is the quantum mechanical model. And the reason it's called the cloud is objects exhibit wave-like behavior. Now, the smaller you get, the more obvious wave-like behavior becomes. On the macroscopic scale, we could say that, yes, we all behave as waves, but that wave behavior is not obvious because of the scale. When you get to a smaller and smaller scale, wave-like behavior becomes more obvious. So when you're on the subatomic scale, wave-like behavior is absolutely significant. Now, why is this important? If something behaves as a wave, what is the location of a wave? Think about that and wrap your mind around that. For example, we can say with certainty where a rock is on the ocean floor. We can point to it and identify the location. But if I see a wave on the ocean, where is it exactly? It's not in one singular location. It's spread out over a region. So I can't just point and say the wave is right there. Well, it's there, and then it's also down the coast, and it's also on down the other side of the coast. We can't identify one location that a wave is. Now, as I mentioned, these subatomic particles, they behave both as particles and waves. And this quantum model, this cloud model, captures the dual behavior by using the idea of probability. The densest area of the cloud, as illustrated on the slide, represents the space of maximum probability of finding a particle. In the case of the electron, the ring of maximum probability occurs at the Bohr radius. So the Rutherford-Bohr model got this kind of right. The maximum probability, or the location of maximum probability of finding an electron, is actually at the Bohr radius. Let's talk about atomic imagery. I already said that you can't see an atom with visible light. Now consider a plane. Let's draw a circle on the plane. Now what if we put 48 atoms along the circle? We can't see the atoms with the naked eye. So what do? A scanning tunneling microscope, which is just an STM for short, employs a sharp tip that is scanned over a surface at a distance of a few atomic diameters, and it does it so in a point by point and a line by line fashion. So at each point that this scanning tunneling microscope is, an electric current is measured between the tip of the microscope and the surface that it's probing. And the variations in the current, as detected by the scanning tunneling microscope, show the surface topology, and the wave nature of matter is revealed. Now this is an image of 48 iron atoms positioned in a circular ring, and it was taken with a scanning tunneling microscope at the IBM Al-Madin laboratory in San Jose, California. So this is a real production, I would say, of research using a scanning tunneling microscope. So this is one way to visualize atoms, and in particular, the wave-like nature of atoms. Those peaks represent the probability, or the highest probability, of finding an atom at that location. The more level regions indicate that it would be very rare to find an atom at that particular location. So the more sharp the peak, the higher the probability of finding an atom at that location. So let's move on to defining some terms. An element is a substance composed only of a single kind of atom. Elements are made of atoms, not the other way around. A pure 24-karat gold ring or bar, for example, is composed only of gold atoms. This is the element. These are the atoms that compose the element. Here's a pencil. The graphite here is the element, and then you have the atoms that compose the element. Now, the word element and the word atom are often used interchangeably, but there is a distinction. Element refers to a type of substance. Atom refers to the individual particles that make up that substance. Periodic table. The atomic number is the number of protons in an atom's nucleus, which is used to classify elements within the periodic table. Now, if you haven't seen the periodic table, here is a picture of it. Let's zoom in on one of the elements. Hydrogen. The atomic number is 1. This is the number of protons in hydrogen. This is the element name. This is the element symbol, and this is the atomic mass. Now, the atomic mass is measured in AMUs, where an AMU is an atomic mass unit, and it's a unit of mass equal to 1/12 of the mass of an atom of carbon-12, which it's equal to approximately 1.66 times 10 to the negative 27 kilograms. Now, of course, I'm not expecting anyone to memorize that number, but in case you want it, there it is. So in the periodic table, from left to right, you add one more electron and one more proton. From top to bottom, you add energy shells. So as you go down the periodic table, you get an additional energy shell. And also, just another rule of thumb, in general, atoms decrease in size as you go from left to right. Now, what are ions? It's an atom with an unbalanced charge. So let's start with the hydrogen atom, because it's a very simple atom. And let's add an electron to it. Before we add the electron, let's just note that we have a positive charge in the center in the nucleus and one negative charge in the electron cloud. So this is a neutrally charged atom. To make it an ion, we add an electron, as an example, which creates a negative ion. Conversely, we could remove the electron, which means that now we only have a positive charge in the nucleus. We have no negative charges, and so this atom has an overall positive charge, making it a positive ion. Isotope. An isotope are atoms of the same element that have differing numbers of neutrons. Again, we will use hydrogen as our example. Hydrogen 1, which is often called protium, consists of just one proton and 0 neutrons. Hydrogen 2 is called deuterium and is composed of 1 proton and 1 neutron. Now, in all these cases, the charge is neutral, and so the electron will stay the same. An isotope is just changing the number of neutrons. You're not changing the charge, you're just changing the number of a neutron. So the chemical behavior of an isotope is the same as just the atom itself, because chemical behavior is governed primarily by the charge. Anyway, going on to hydrogen 3, tritium, you have 1 proton still, because if it's hydrogen, you have to have the same number of protons. If you change the number of protons, you no longer have the same element type anymore. In all these cases, the number of protons is the same, in this case 1 proton in every case, because an atom with 1 proton corresponds to the element hydrogen. So these all are hydrogen. I'm just changing the number of neutrons in the hydrogen atom. Molecules. The smallest group of a substance consisting of 2 or more atoms held together by chemical bonds. Oxygen is an example. This would be a diatomic oxygen in particular, and is considered a homonuclear molecule since it consists of 1 chemical element. That is, well, oxygen. There's only 1 type of atom here. Also, ammonia is a molecule, NH3, as is methane. Now, ammonia and methane are considered heteronuclear molecules because they are chemical compounds consisting of more than 1 atom type or more than 1 element. Oxygen is, again, homonuclear because it's just 1 element type within it, just oxygen. Ammonia and methane are heteronuclear because they have more than 1 element type. Ammonia has hydrogen and nitrogen. Methane has carbon and hydrogen. Compounds. A substance composed of many identical molecules containing atoms from more than 1 chemical element that held together by chemical bonds. So here we have sodium chloride on the left, and on the right we have sodium carbonate. Now sodium is represented in purple here, chlorine is represented in green, carbon in black, oxygen in red. Compounds have elements arranged in a fixed order and proportion. There's a repeating pattern to them. This is very important because this is going to be distinct from mixtures. A mixture is a substance mixed together without chemically bonding. So there's no repeating pattern here. If you take a small sample of a mixture, you're going to get a different proportion of the atoms that compose that particular mixture. Examples of a mixture: air is an example of a mixture, wood is an example, the smoothie that you make for breakfast is an example. A mixture is not the same thing as a compound. A compound has a repeating structure pattern to it. A mixture is not, there's no pattern to this. Antimatter is simply matter composed of antiparticles, which have the same mass as particles of ordinary matter, but have opposite charge and quantum spin. So we're not going to talk about quantum spin, but just know that antimatter has the opposite charge of standard matter. So for example, let's look at hydrogen once again, and then we'll look at antihydrogen. So hydrogen, we have the proton, electron, and neutron. Antihydrogen has some things mixed up. In the nucleus, we have the antiproton, so the same mass as the proton, but negative charge. And then the orbiting cloud is now, instead of having a negative cloud, we have a positive orbiting cloud because the anti-electron, also known as the positron, is now the particle that is orbiting. Now the neutron, which has no net charge to begin with, is, as we mentioned before, composed of quarks, which have charge. So the antineutron, just as with the antiproton, has antiquarks in it. Now with the neutron and antineutron, they're still neutral, but the quarks within them are different, because in the neutron you have standard quarks, and the antineutron you have antiquarks. Importantly, if matter and antimatter meet, they annihilate each other and release radiant energy. Mass is converted 100% into energy, just as Einstein's famous equation states, which is E equals mc squared. Now, the observable universe is almost entirely composed of ordinary matter and not much antimatter. And this is actually, this asymmetry remains a mystery to this day. It's one of the grand mysteries that scientists still wish to uncover. They want to know, why is it that we have so much matter but almost no antimatter? In summary, we discussed Brownian motion, atomic models and structure, the periodic table, atomic variations, elements, compounds, and mixtures, and antimatter. I will see you next time.